Hi everyone, in this video we're going to be solving for acceleration using Newton's second law for 3 different examples. Coming right up. In today's video we will be solving for acceleration of two forces. Let's pretend we have one person pushing a box east and another person pushing it north. The person pushing the box east, we're going to call this force 1 and draw it on our x-axis. It is going to be 20 newtons, and the force 2, which is going north and on our y-axis, is only 15 newtons. So the person pushing east, we can pretend it's a bit stronger than the person pushing north to put it in some perspective. We will also assume that the mass is 2 kilograms. To start these types of problems, before I start writing any equations, I like to figure out an expectation of my result. If we're solving for the acceleration, we need to get a magnitude and a direction here. I will assume in this case the box will start traveling somewhere in the northeast direction. Since force 1 is the one going east and it is a little bit bigger, I also expect the acceleration to be closer to my horizontal, or my angle theta to be smaller than 45 degrees, which is halfway between force 1 and force 2. So now, let's start by getting our horizontal force and vertical force components to see if our expectation here is right. Since only force 1 has any horizontal component and force 2 has only vertical components, we can then conclude that f of x is just f1, and the same applies to f of y, is just going to be f2. If any of these forces had any angle between the horizontal and the vertical, then we'll have to account for both components of that force, but not the case in this example. We'll see in the next two examples today. I will also like to write the Newton's second law equation so we remember how to solve for the acceleration, which is just F equals to ma, or acceleration equals to force over mass. So now we can solve for my acceleration of the horizontal component and my acceleration of the vertical component. We'll just do F1 over m for the first one and F2 over m for the second one. Once we plug in our numbers, we can see that 20 newtons over 2 kilograms is just my acceleration for the horizontal component, which is going to be 10 meters per second square, and the same for the vertical is just going to be 7.5 meters per second square. Now, how do we actually get the acceleration from here? So since we have the vertical and the horizontal components of the acceleration, all we need to do is go back to our Pythagorean theorem, where it states that for a right angle triangle, we can add the horizontal square, or a square in the triangle, plus b square, or the vertical square, and then we'll get the hypotenuse square, or c square. By doing this here, we're adding the horizontal and vertical components squared of our acceleration and getting the magnitude of the acceleration squared, so we just have to square root it at the end to get the magnitude of the acceleration, just like is shown in the equation there. So after solving for all this, we can get that the magnitude of the acceleration is 12.5 meters per second square. We also need to find the direction. Remember, we can solve for the direction by getting the angle from the horizontal. Now, we need to also use trigonometry here. We have the vertical and horizontal, so we can actually get the angle by solving our known tangent equation, where tangent of theta equals the opposite over adjacent. Since we are solving the angle from the horizontal line, we know that the opposite is the vertical and the adjacent is the horizontal. Just look at the triangle from the angle's perspective, as if we were standing on top of the theta. We can see that in front of us will be the vertical line, and under us, or standing on it, will be the horizontal line. Then to rearrange this equation to find the angle theta, we need to solve for the inverse tangent of opposite over adjacent equals to theta. We can see that the angle is exactly what we expected. 36.9 degrees is on the northeast and less than 45 degrees. Perfect. Now let's work on a different example. In this new example, we will be getting the same magnitudes of the two forces. So F1 is again 20 newtons and F2 2 is only 15 newtons. However, force 1 is also going east as before, while force 2 is going northeast, 60 degrees from the east direction. What is our expectation here for the acceleration? We expect the direction to be even closer to the horizontal. Since both forces have a horizontal positive component, they both are going east. Also, we can expect then that the magnitude to be higher than in the previous example, because we have two people pushing the box almost in the same direction, so you can basically add the forces horizontally somehow, and it makes it stronger than having one person going north and the other person east. So now let's see if we're right here. Again, we have to find the horizontal force component and the vertical force component like last time. The horizontal force component also has F1 like previously. However, F2 also counts with horizontal component. We know that cosine of the angle is the adjacent component. So again, let's pretend we're standing on theta angle. We can see we're standing on the horizontal, also known as the adjacent of a force 2. So we can add F2 cos theta. For the vertical force, we can now again assume F1 has no vertical component, but F2 has some vertical component. It is now the opposite of the angle theta, so it is a vertical, it's just F2 sine of theta. We can now solve for the vertical and horizontal components of our forces, and we get the horizontal component to be 27.5 newtons, and the vertical component is only 13 newtons. Now, let's solve for the acceleration components just like the previous example. Again, we can get the acceleration magnitude by applying the Pythagorean Theorem. The magnitude is then 15.20 meters per second square. To get the direction, we just solve for the inverse of the tangent of the vertical acceleration over the horizontal acceleration. And we get the theta angle of the acceleration to be equal to 25 degrees. Was this like we were expecting? Yes, our magnitude is bigger than last example, and the angle is closer to the horizontal. In this case, we have 25 degrees, which is a little bit smaller than the 36.9 degrees we got previously. Now, let's move on to a different example. Remember, practice makes perfect. In this example, again, the two magnitudes are the same, 20 and 15 newtons, so 20 for F1 and 15 newtons for F2, and the mass remains 2 kilograms. Force 1, just to keep it consistent, is going east on our positive x-axis, and force 2 is now going to the northwest direction, 60 degrees from west. So it is 60 degrees from the horizontal. In this case, we have one force going on our positive x-axis, and the other force is actually going on the negative horizontal. What can we expect here? Well, we can expect the magnitude to be smaller than the acceleration in the previous two examples. Why? Because we have people pushing the box in almost opposite directions right now. Also, the angle is still going on the northeast because the force 1 is bigger than force 2, but the angle is going to be a little bit higher, so closer to probably to my north side, to my y-axis. But let's find out if that's right. So now let's solve for the horizontal force component. We can again add F1, and since F2 is going in the negative horizontal direction, because we are considering my east side to be the positive, then west is negative. I have to subtract my component, horizontal component of F2. Then the vertical component is this positive or negative. It is again going to the north or up in our map. We have always considered up or north to be positive in our examples. So Fy is the same as our previous example. It is positive F2 sine 60. We can solve for the forces here and solve for the accelerations to get acceleration x, or the horizontal acceleration, equals to 6.25 meters per second square, and acceleration vertical is 6.5 meters per second square. Do you notice how they are almost the same? Also, the horizontal for the first time is smaller than the vertical component. In our previous examples, we were able to see that horizontal acceleration was much greater than the vertical, not in this case. The magnitude of the acceleration is then 9.02 meters per second square, which is smaller than the other two examples we just solved, as we were expecting this. Now, solving for the inverse tangent, we see that the angle of the acceleration is 46 degrees, which again makes sense that it is greater than the first and the second example, since the vertical component is a bit stronger than the resultant horizontal in this example. So that's it for these 3 examples. In the next video, I'm going to be solving more complex problems. Please don't forget to subscribe and let me know if you have any questions. Thank you.